Howdy, and welcome to Week 1, Lecture 1 of EET 260 Microcomputer Applications for the Spring 2021 semester. I'm Jeff Cooper. I'll be your instructor for this spring semester, and we will be diving into all sorts of microcontroller applications, and of course, so the obligatory thing we have to do is we have to go over the syllabus in our first lecture, which is a lot of fun. But maybe first I should tell you a little bit about who I am. And so I've been an electrical engineer for, I'd like to say, 100 years. And then decided to, I always wanted to do some teaching, kind of share the wealth, as they say. And so I, like 10 years ago, through a divinely inspired process, I came to STIC. And one of the people that hired me in was Professor Jagodowski, who is just really sharp with these all this electrical curriculum and everything, electronics curriculum. He's really kind of gifted in, I think, in the way he finds things and brings them into use. And so this is the kind of thing between microcontrollers and programmable logic. My career has been structured on both of those things really strongly. They're two of the most general purpose, flexible, programmable, innovative things that you can put in the middle of an electronic system. And so we're going to talk about microcontrollers for sure. And we'll even talk a little bit about the history and all that sort of thing. But mostly we'll get into programming them and making them do stuff, turning on and off lights and spinning motors and sensing temperatures and all that kind of thing. And Professor Jagodowski will teach the lab for this course, where all the fun things happen, and I will teach the lectures where all the boring kind of stuff goes on. It's not boring, really. I love this stuff. That's why I wanted to teach it, is that microcontrollers made a great career for me, and so did programmable logic. So bearing that in mind, and with all the enlightenment there to ascribe, let's dive into our course syllabus. So now you know who I am. I have an office in building 17, and I have an office phone, but I would highly recommend not using this phone. Please use the email address, because during this COVID thing, I duck in for an electronics lab on Monday afternoons and a biomedical systems lab on Wednesday afternoons. But other than that, like most of you, I'm at home. So and eminently online all the time. So please use the email. The course has a Blackboard Learn site, and this is supposed to be a link to that. You know what? If this is not a link, which it appears to not have come through from Word into the PDF as a link, I will post this link. No, I won't, because you need the link to get to where I'll post it. Anyway, this is the Blackboard Learn site for our class. The class modality is distance. Some people term this as asynchronous, meaning you can watch the videos whenever you want. We don't meet at any set time, either in person or online. So I will post lectures and assignments and stuff to the Blackboard Learn site. And you pick those things up, and you can submit your homework back through the site. And as far as office hours go, I'll post something on the class Blackboard Learn site, but just email me. One of the benefits of this, you know, distance asynchronous format is that we can arrange and have a Zoom meeting or Google Meet or whatever, and go over something if you're kind of stuck with it. So just know that that's there. I think we'll post some hours, but you don't feel that you have to be constrained to those hours. We'll work back and forth. Sometimes questions can be answered in email, and I can put a couple pictures in the email or screenshots or something, and that may get you going. There's no required textbook for this class. All the documents provided in the course, Blackboard Learn website, provided above. So there are actually kind of like textbooks in there. There's a lot of manuals from Parallax, the makers of your Bobot that you used in a previous course. We'll be using that, and we'll be connecting things to it and interfacing to it. So you've already had some experience with microcontrollers with your Bobot kit. You programmed them and everything, but now we'll take it up a notch in terms of interfacing and using them in a system, and kind of get you started on that sort of thing. The course description is from the STIC website. This course is directed to the application and use of microprocessors in industry, really microcontrollers, and we'll talk about the difference between them. With emphasis on understanding basic operation, interfacing, and programming, the study includes basic architecture, developmental languages, bus structures, interfacing with peripheral devices, memory input and output devices, and diagnostics. So we will actually cover all those things. They're just the natural. Lingua franca of using microcontrollers, and microcontrollers are in everything nowadays. And I think you already know that. You are supposed to have taken MAT 125, which is Technical Math 2, and EET 200. If this is not the case, then you've probably made an arrangement with Professor Jagodowski to register. The co-requisite is the lab for this course, no surprise there. And the student learning outcomes, again, I think it's from the STIC website. Analyze various types of microprocessors, no microcontrollers, but have a knowledge of and be able to select and operate appropriate microcontroller-based equipment. So like, if taking a microcontroller on a board and hooking it up to a personal computer and maybe downloading some code to it, or maybe even in the field, you take a laptop around with you and you update code, you make modifications as whatever company you're working for indicates. Maybe you even load in data that's specific to that customer's use, or all sorts of things, some of which you probably already have done to some degree, and this course is meant to cement that and extend it. The idea also being number 3 here, for you to see that every time you look at one of these drive controllers for AC motors and stuff, you can see that there are displays on the outside and buttons you push, and maybe even the GE ones have a little removable terminal that has a micro in it, and the drive controller has a micro in it, and you can program parameters from that thing, or you can, some of these I'm sure have either some Bluetooth or some kind of serial or USB connection that allows you to do that kind of thing. And as a technician, you care about the microcontroller stuff as you're learning it in this class, but then also, what does this box do in the bigger world? What's it part of, and what do I need to consider when I change something here? How does it affect the other stuff downstream? Like, if I set this roller up to a higher speed, then I suppose something down the line has to be able to handle that speed, or being part of a bigger system, and all the considerations thereof. Number 4, to gain a basic knowledge of the maintenance, installation, programming, and upgrading of various microprocessor controlled, let's call that microcontroller again, system components defined for industrial tasks. Yes, you want to be able to take a microcontroller system and not only maintain it if that's required. It might be setting parameters. It might be calibrating it once in a while to make sure it operates near some standard. You install them just like you install PLCs or that kind of thing in a factory automation thing, or in a building, maybe a building heating, ventilating, air conditioning system. You install these things, you program them. Occasionally upgrades come out and you have to maybe go visit them, or maybe they're on the web on the internet, and you can reach them and access them. So just that whole operation of what technicians do with these microcontroller based boxes, what do technicians do is they install them, configure them, and maybe even troubleshoot them as well. Well, not maybe even, but certainly troubleshoot them as well. To provide the student with information and expertise in the area of microcontroller-based system troubleshooting, there we go, and maintenance for a variety of applications utilized in manufacturing. And manufacturing is a great application area for microcontrollers. What you would learn in here would carry over, whether it's into, I teach biomedical engineering technologies, and microcontroller boxes dominate in that field as well. And if you were in, mining, or if you were in defense, or if you were in, transportation, these same skills would transfer to each application area of microcontrollers. Avionics and airplanes, it's just all sorts of things. The competencies, we're going to talk about analog and digital signal processing, because the microcontroller is a digital device, but the world is analog, so we'll do that. And we'll integrate that with some digital logic, so that while we talk about analog to digital converters and digital to analog converters, we'll also talk about how that works with the with microcontrollers in the digital realm. We'll analyze devices utilizing embedded controller devices. That's kind of a restatement of some of the stuff above. There'll be a box with a microcontroller in it. And this idea of embedded we'll talk about, it just means that someone has taken a microcontroller and put it on a board and embedded it inside some box that does something specific, as opposed to a general purpose computer, like a laptop or a server computer or a desktop computer. Embedded systems, although they can do a wide variety of things, are not designed for general purpose computing, for office use or scientific use or that sort of thing. They are focused toward a specific goal, and that's where that embedded system is going to go, be it an engine controller for an automobile, or some kind of logic controller in factory automation, or HVAC temperature and humidity control. So you'll take a look at some of those kind of things. Effectively read and write the command set of the BS2 series of processors. This is the basic stamp 2. That's what you use in your Bobot. So we're just going to take one example of a microcontroller, the BS2, and do a lot of things with it. Read and create flowcharts. Actually, pretty simple to do, and I think you'll master that quite quickly. It's something that I'll make sure that we do, even when we do something really simple. We'll talk about what the flow of the program is in the microcontroller. Analyze and diagnose systems with basic and advanced sensor I/O, including smart sensors. Yep, we're all about that. We'll be using different sensors and getting them hooked up to our basic stamps. Create basic embedded controller interface circuits. That's more of the same. Read and create schematic diagrams. I think you already do this, but we're going to just take it a little further, and those schematic diagrams will now include wires that connect to a microcontroller. And I'm sure you've seen some of that or at least kind of comprehended it when you made your Bobot. Apply a systems level view of complex systems for troubleshooting purposes. Always want to do this in every electronics course. In every technician course in every discipline, we want to think about what is the flow of the elements in this system. In other words, if we could make a block diagram of the system and things worked in one place and didn't work in another, what does that tell us about where we want to look for problems? And it's really what they like to call critical thinking, but at a pretty, sometimes at a pretty simplistic level, and it gets more complicated with the system. But you have to start at the basics. Where are things good? Where are they not good? What could cause what I'm seeing, and then you troubleshoot the system, based on those things. Now here's the expectations part. Students should regularly access the class materials in the Blackboard Learn site. This is important because it's for one thing, it's our only way of knowing if you're participating in the lecture part of the course, and it'll show up in the laboratory part too. If you haven't followed along with the lectures, because I try to gear this stuff right toward Professor Jagodowski's lab sequence. So we try to talk about the things that you're going to be using in lab with the basic stamps. All email correspondence needs to go through the STIC email facility. In other words, your student.stic.edu email is the only email I'm supposed to recognize from you, and I'll remind you if you accidentally send something from a personal email. If it happens once or twice, I'm likely to read it, and I'll just remind you, please use the school email. And it'll seem like I'm being kind of sticky and picky about the thing, but it's just it's what we have to do. And please, and I put must. I can't, with all the different courses I teach, if you can put EET 260, I don't know if the DO1 is necessary. There's only one section of EET 260, but if you can get EET 260 at the beginning of your subject line, that will help me greatly. And it'll also get you a response faster than if you don't do that. Only because, if I have to go look up, who this is and from what course it is, then it just takes time. And please, I should also put in here, try to make your email questions have some specificity. Just make them specific is the short way to say that. Yes, please make them specific, and that way we can talk about things that we can name and describe in emails. And a lot of times, the kind of unstructured and confusing stuff, if you can name some of the individual aspects of where you're having a problem, it actually help you too. You'll ask better questions, and you'll move through the stuff faster. And it's just part of the work that's necessary to do to learn the stuff, is to kind of really work on trying to make some progress, and then make your questions be specific. Students need to keep pace with the online course delivery of this lecture section in order to be prepared for the concomitant lab section. I think we already said that. You got your code of conduct. It's available from the STIC website. Students must also keep apprised of the STIC academic calendar. And the STIC academic calendar, in case you don't know, it's let's go out here to the glorious STIC website. And here's the STIC website. Now, right here, there's a thing that says calendar. You click, you go down, academic calendar, and this thing tells you, what special days are set aside for this, that, and the other thing, when advising happens and when exams happen, and what days are not. A STIC is not in session, so if you have a laboratory on a specific day, of course, Professor Jagodowski will address that, but you need to be aware of this academic calendar. And due dates, late work may be depreciated. 25% every week, or part of a week it is late, and if we post solutions, then we're not going to accept homework after the solutions are posted for rather obvious reasons. And poor quality work will not be accepted. You need to format your work in a readable way, and it needs to show a significant attempt to solve each problem. So bear that in mind. Also, no one's able to read anyone's mind, so it's pretty important to put what you're saying in your homework assignment work, and so that we can grade it and look and say, oh yeah, the more logical and significant your attempt is, the more we can appreciate what you've done. Academic honesty, I'm sure you've experienced this paragraph before if you've taken any classes in the EET program at STIC. Basically, don't cheat and don't let other people cheat off you, because everybody loses. All right, I'll let you read that paragraph exactly on your own, but that's basically what it says. Don't cheat, don't let people cheat off you, and do good work, and be in touch and stay healthy. Attendance policy. Well, it's an online course. We don't have to do much there. We have a grading policy. We have 2 exams at 20% each, and a number of homework assignments for a total of 60%. And so that will add up to your grade. We have the STIC grading scale, and the exercises assigned during the course assignments will be accompanied by rubrics in the assignments Blackboard Learn assignment entry. So when you find an assignment there, unless it's the simplest kind of assignment where it says, maybe a vocabulary list or something like that, you don't need a rubric for it. Well, maybe you do, I don't know. But, we'll try to give you some ideas as to what it takes to get the best possible score in the answers that you supply. The course schedule here, we're going to go over a course map in just a minute. I'll do that just in a separate video to break these things up. But, this week we're talking about the syllabus and the policies, and we'll do an introduction to the course. And then we'll talk about, as the weeks go on, we're going to be kind of doing a whirlwind review with a little bit of new material, but mostly a whirlwind review of What's a Microcontroller, the book that you use to build your Bobot. And by the time we approach midterm, we'll be talking about new things, as chapter 5, 6, 7, and 8. And then we'll start to talk about the advanced sensors that we mentioned in the student learning objectives. And for the following weeks, we'll just be talking about taking our microcontrollers and interfacing them to new and different things. Toward the end of the course, we'll talk about trends in microcontrollers, the Internet of Things, Propeller. I don't know if we'll really talk about Propeller. It's a canard of a it's an unusual architecture for a microcontroller, and there is a Propeller 2 out now, so it's kind of interesting. Maybe we'll look at it from the standpoint of it's actually a bunch of little processors that can run in parallel. The Raspberry Pi, of course, is it really strains the definition of microcontroller because it runs an operating system like Linux. And so the microcontrollers have become so powerful nowadays that they are beginning to blur the distinction between general purpose computing and embedded computing. And we'll talk about industrial IoT and the networking and system security topics, which you can imagine are pretty much the focus of consternation nowadays. You start putting control systems that can control pretty large capital investments or have human life implications in a network, and someone hacks in and is able to get control of them. That could be a bad day for everybody involved at that end of the thing. And we may modify this thing. We may move the topics around. But as you can see, these topics, we have a lot of flexibility in which sensors and interfacing structures we should say that again. Which sensors and which interfaced devices we talk about in these weeks here. We have a lot of flexibility in that. The standard Office of Disability Services statement is included here. You should contact them if you feel you have a documented disability, and their information is placed right there. And we will do everything we can to accommodate any such thing. And accommodate is just an entry-level word. We will really try to make sure that you're fully involved, regardless of who you are. And especially if you like this stuff, you'll find that we like it too. And the engagement will be at a pretty high level. So look forward to that. In the next video, I'll talk about our course map again, which will recapitulate this schedule a little bit, and then we'll get on to our first introductory lecture. So thanks for listening, and we'll talk to you soon. Bye.